Welcome to the video key for quiz 1. Number 1. Consider two light waves, one with short wavelength and one with a long wavelength. Which one has the higher frequency? Alright, so we want to relate wavelength and frequency. So we have the equation frequency times wavelength is equal to the speed of light, nu times lambda equals c. And we can also say that there's a reciprocal relationship between nu and lambda, that they're both, since the product is a constant. So nu, we could say, is equal to c divided by lambda. Okay, so that means the shorter the wavelength, the greater the frequency. Okay, so if one goes up, the other goes down. So we want something with higher frequency. The way to get that is to have a shorter wavelength. Number 2, consider two light waves, one with a short wavelength and one with a long wavelength. Which is the higher speed? Well, these are both light, so they have the speed of light c, right? C is a constant, so we can look this up on our equation sheet, and we can see that for any kind of light, c is equal to 3.0 times 10 to the negative 8th, or 10 to the 8th rather, 10 to the 8th meters per second. Okay, so if we're traveling in a gas or in a vacuum, this doesn't matter what kind of light we have, whether it's microwaves or visible light or UV. They're all going to be the same. Number 3, consider two light waves, one with a short wavelength and one with a long wavelength. Which is the higher energy per photon? So energy is equal to the Planck's constant times the frequency, so h nu. Now we don't have the frequency, we have the wavelength. But we know that we can relate wavelength to frequency because wavelength times frequency is going to give us the speed of light. So we can solve this for frequency, so we get frequency c over lambda, and then we can substitute that expression for nu, for the frequency, with c over lambda. And that gives us the energy of a photon is hc over lambda. And now we can see that the energy of the photon and the wavelength are reciprocal, right? There's a reciprocal relationship. If one goes up, the other goes down. So if we want a higher energy per photon, we want a smaller value of lambda, right? So the shorter the wavelength, the higher the energy. And so we can look at the frequency of various forms of light. We won't do all of them, but like ultraviolet, we can see that's going to have more energy per photon than visible light, and that's going to have more energy per photon than infrared, and more than microwave. So as we go to, if we start off with short wave lengths of light like ultraviolet, with a longer wavelengths of light like microwaves, we're going to less energy per photon. So shorter wavelength, higher energy per photon. Number 4, calculate the frequency of a photon with energy 2.1 times 10 negative 22 joules. So we have energy is equal to h nu. We want the frequency, so we have to solve for frequency, so we divide both sides by h. To get energy divided by Planck's constant h gives us the frequency. Now we're going to plug in our energy, 2.1 times 10 negative 22 joules. And that's the energy of a single photon. We're going to divide it by Planck's constant. So we can find this on the equation sheet at 6.626 times 10 negative 24 joules times seconds. So be careful, it's not joules per second, it's joules times seconds. All right, once we do that, we should check to make sure the units cancel properly. So joules cancel. We've got 1 over seconds, or reciprocal seconds, and that is the right unit for frequency. So we're ready to go. So we can plug in our numbers. And we plug those in around just a 2 sig fig, since that's what our data is. We get 3.2 times 10 to the 11th reciprocal seconds. And that's the right units for frequency. So it looks like we're done. And we're dividing a small number by an even smaller number in our numbers. And so you divide by something really, really small, we should get a bigger number. And indeed we do. We get a relatively high frequency. So that's it for the video key for quiz 1. Thanks for watching.